Welcome to the wonderful world of physics. This is the Chapter 20 homework solutions for Physics 102B. Let's take a look at number 26. Find the wavelength ranges for AM radio, and it gives the frequencies, and then for FM radio with the given frequencies. On this page, we'll look at AM radio. So the given frequency range is between 540 and 1600 kilohertz. If we want to find the wavelengths associated with those frequencies, we'll use this equation. Speed of light is wavelength times frequency. And so we solve for lambda, which is wavelength. That's the speed of light divided by frequency. And let's do the first given frequency. Lambda is 3 times 10 to the 8th meters per second divided by 540 kilohertz, which is 540 times 10 to the 3rd hertz. And as you look at the units, remember that a hertz is a per second. So we have in the numerator per second and in the denominator per second. Those will divide out and we're left with just meters. And so for that frequency, lambda is 555 meters. For the higher frequency, we have lambda is 3 times 10 to the 8th meters per second divided by 1600 times 10 to the 3rd hertz, and we get 188 meters. So let's reverse the order of those. And so we have a frequency from the lowest frequency to the highest, the wavelength from the lowest to the highest is 188 meters to 555 meters. With FM radio, we have a much higher frequency range. So we have between 88 and 108 megahertz. We'll use the same equation that lambda is the speed of light divided by frequency, and we're just plugging in these different frequencies. So for the low frequency in the range, 88 times 10 to the 6th hertz, and that gives us 3.41 meters. For the higher frequency in the range, lambda is 3 times 10 to the 8th meters per second divided by 108 times 10 to the 6th hertz, and we get 2.78 meters. So as we give the range, let's do it in order from lowest to highest. The wavelength range for FM radio is 2.78 to 3.41 meters. Number 34 says for electromagnetic waves with each of these frequencies, find the wavelength in a vacuum. In what region of the electromagnetic spectrum does each lie? So part A, we're going to use the formula that we used in the previous problem. Lambda is speed of light divided by frequency. And we plug in that first frequency, which is 9.4 times 10 to the 12th hertz. And we get 3.2 times 10 to the negative 5 meters. Now the question is asking in what region of the electromagnetic spectrum does each lie? And I encourage you to look on page 475 of the textbook, the Chapter 20 summary. There is a table of the different wave types and frequencies, and there's also a chart that shows them. And so locate either the frequency or the wavelength, depending on what you're looking for. And you should see that this frequency falls in the infrared. In the table, it says that infrared is between 10 to the 12th and 4.3 times 10 to the 14 hertz. And so this falls in the infrared. For question B, it says 6.2 times 10 to the 14th hertz. And so we'll use the same equation. We get a wavelength of 4.8 times 10 to the 7 meters. And we look in the chart and we see that this falls in the visible realm, which is between 4.3 times 10 to the 14th and 7.5 times 10 to the 14th. So that's visible light. And by the way, there's also in the book, table 20.1 shows that specifically this wavelength, 480 nanometers, is actually between blue and green. The next one has a frequency of 2.9 times 10 to the 15th hertz. So progressively, these frequencies are getting higher and higher. And we get a wavelength of 1 times 10 to the negative 7 meters. And we look in the chart and we can see that that's going to fall in the ultraviolet. And finally, we have a frequency of 5 times 10 to the 17th hertz. Plug it into the equation and you get a wavelength of 6 times 10 to the negative 10 meters. And you look on the table in the back of the chapter and it says that X-ray is between 10 to the 17th and 10 to the 20 hertz, so this would be X-ray. Number 35 gives the wavelengths, and we're to find the frequency and in what region. So we use the equation frequency is speed of light divided by wavelength, and we'll start with part A, 2 kilometers, so 2,000 meters, and that is 150 kilohertz, which is radio. Part B is 2 meters, so we get 1.5 times 10 to the 8th hertz, which is also radio. For part C, we're going to divide the speed of light, 3 times 10 to the 8th meters per second, by 2 millimeters, which is 2 times 10 to the negative 3 meters. We get a frequency of 1.5 times 10 to the 11 hertz, or 150 gigahertz, and that's microwave. Part D, 2 micrometers, 2 times 10 to the negative 6 meters, gives us 1.5 times 10 to the 14th hertz, or 150 terahertz, and that's infrared. And finally, part E is a wavelength of 2 nanometers. Plug that in, 1.5 times 10 to the 17th hertz, or 150 petahertz, and that's in the X-ray. Number 41, an electron is moving at 0.99 times the speed of light directly toward a light source. In the electron's reference frame, how fast is the light approaching? There's no math needed here. Light moves at 3 times 10 to the 8th meters per second in all inertial reference frames. So in the electron's reference frame, it's moving at the speed of light. Number 44, a rod with a proper length of 10 meters. So we're going to write L naught equals 10 meters, lies in the x-axis. If the rod is traveling in the positive x direction, find the rod's measured length when its speed is, and there are these 4 choices. So we're going to use the equation for length contraction, that length is proper length divided by the gamma correction factor. And in part A, here I have the gamma correction factor. It's 1 over the square root of 1 minus v over c squared. So the v over c is 0.1, and we get a gamma correction factor of 1.00504. Therefore, the length is 10 meters divided by that correction factor, so it's been shortened down to 9.95 meters. At half the speed of light, first do as I did in part A, find the gamma correction factor, which is 1.1547, and then the length is 10 meters divided by that, so 8.66 meters. Part C, at 9/10 the speed of light, we get a gamma correction factor of 2.294, and so the rod is shortened to a length of 4.36 meters. And at 99% of the speed of light, the gamma correction factor is 7.089. And so the length of the rod is 10 meters divided by that gamma correction factor, so 1.41 meters. Number 45, a spaceship flies from Earth to the Moon, a distance of 400,000 kilometers. Find the elapsed time for this trip both on Earth and on a clock on board the spaceship when the ship's speed is, and there are these 4 different parts to it. So let's look at part A. The distance is 4 times 10 to the 8th meters, and the speed 0.01 c for part A, so that's 3 times 10 to the 6 meters per second. From Earth's point of view, the time is simply distance over velocity, because in Earth's reference frame, it's going that distance, 4 times 10 to the 8th meters, and it's going at the speed of 3 times 10 to the 6 meters per second, and so we get 133.3 repeating seconds. For the spaceship, there's a gamma correction factor of 1.00005. And so the time as measured on Earth is gamma times the proper time. Proper time is on board the spaceship. So we're going to solve for proper time, delta t over gamma, and we get 1.005 or I'm sorry, 133.33 repeating seconds divided by that gamma correction factor of 1.00005, and we get 133.326 repeating seconds. You'll notice that the time on board the spacecraft is just a little shorter, and that's a good check because sometimes we might make a mistake and divide the wrong time, solve for the wrong time, but then you just think on board the spacecraft that's going fast, its time is going to be shorter than the time on Earth, so it should be shortened. For parts B, C, and D, we just do that, but for different speeds. And so at 0.3 times the speed of light, we get that that's 9 times 10 to the 7th meters per second, with a gamma correction factor of 1.04828. And from Earth's point of view, the time is the distance divided by that new velocity, 4.44 repeating seconds. For the spaceship, we're going to take that time, the Earth time, and use the gamma correction factor. So the proper time is the Earth time divided by gamma, 4.240 seconds. For part C, the spaceship is now going at 3/4 of the speed of light, 2.225 times 10 to the 8th meters per second with a gamma correction of 1.51186. So from Earth's point of view, distance divided by velocity, 1.78 seconds. On the spaceship, divide that time by the gamma correction, it's 1.176. Notice as we've gone from parts A, B, and C, as we do a faster and faster spacecraft, there's a larger gap between the Earth-based time and the spacecraft time. Finally, for part D, we're at 99% of the speed of light, which is 2.97 times 10 to the 8th meters per second with a gamma factor of 7.0888. From Earth's point of view, 4 times 10 to the 8th meters divided by 2.97 times 10 to the 8th meters per second, 1.35 seconds. With the gamma correction factor, the spaceship clock reads 0.190 seconds. Number 46, our galaxy's diameter is about 10 to the 5th light years. How much time does it take an electron moving at 0.9999 C to cross the galaxy, measured in the reference frame of the galaxy and the electron? One way we could do this is convert everything to MKS units. Convert the light years to meters, convert the speed, use 3 times 10 to the 8th meters per second. But it's easier to do it this way, to consider the speed of light, rather than think of it as 3 times 10 to the 8th meters per second, to think of it as a light year per year. That's what the speed of light is. It's 1 light year per year. It's much easier if you use those units. So from the galaxy's point of view, the time for the electron to cross it is distance that it's traveling in the galaxy's reference frame divided by velocity. So we have 10 to the 5th light years divided by 0.9999 light years per year. And so we get 100,010 years. For the electron going at that speed, there's a gamma correction factor of 70.712. So we're going to solve for proper time just as we did in problem number 45. And we get that the 100,010 years have been shortened by the gamma correction factor to only 1,414 years. Number 48. You want to gain a year on your earthbound peers, traveling fast enough on a round trip that when 10 years elapse for them, only 9 years elapse for you. What speed is required? So we want to think about our proper time on our ship is 9 years. The time for the outside observers on Earth is 10 years. Time is gamma times proper time, so we're going to solve for gamma in this case, 10 years over 9 years, which is 1.111. Now we want to see what speed is going to give us a gamma factor of 1.111. So I go through the algebra here. You can follow along. We start with gamma equals 1 over square root of 1 minus v over c squared. and I take the reciprocal of both sides, square both sides, I end up with a speed of times the speed of light, square root of 1 minus gamma to the negative 2, square rooted. And so we can plug those in and we get 0.436 times the speed of light, or 1.31 times 10 to the 8th meters per second. Now, as we learned about with the twin paradox, this strategy won't actually work, because if you're doing a round trip, then the special relativity equations don't work anymore. You need more complex equations of general relativity. And so this isn't going to work. And furthermore, when you think about if you're just going in a straight line, not accelerating, that from your point of view, their time will be shorter. So this strategy actually will not work. Number 50, in the future, speeding tickets for spaceships will be issued based on the spaceship's measured length. This spaceship has a proper length of 75 meters. The posted speed limit is 0.6 c. Will the spaceship be ticketed if space police measure its length at 65 meters? All right. So proper length is 75 meters. Observed length is 65 meters. And we want to see what speed is that going. And you can go back to problem number 48 and see my derivations. First of all, let's figure out what the gamma needs to be. Gamma is proper length over length, 1.1538. And again, I want to remind you that if you find yourself ever in any problem like this, relativistic problem, getting confused, asking yourself, which one do I divide? I'm not sure. Well, gamma will always be greater than 1. So you have a 50-50 guess at what you're going to divide. If you guess incorrectly, you're going to get a number less than 1. So that just tells you you did the wrong ones, and so do it so that gamma is greater than or equal to 1. So here we have 1.1538, and you can look back to problem number 48 for my derivation, but the speed is speed of light times the square root of 1 minus gamma to the negative 2. And we end up getting 0.499 times the speed of light. Now, because the speed limit is less than, because this is less than the speed limit, which is 0.6 times the speed of light, then there will be no speeding ticket. Number 53, a linear accelerator can accelerate subatomic particles to close to the speed of light. A proton travels through 1 kilometer section of the accelerator with a constant speed. Find the proton's speed if this section is only 1 meter long in the proton's reference frame. So the proper length, which is the distance of the tunnel it's going through, is 1,000 meters. And that distance, that length, is going to whiz by the proton. The length as measured by the proton, so here we're considering the proton to be the outside observer, and it's this length of tunnel that's coming at the proton. So the length of the tunnel as measured by the proton is 1 meter. Well, length equals length, proper length divided by gamma. So gamma is proper length divided by length, and so we get a factor of 1,000. That's going to be very, very close to the speed of light. We can then use the derivation that we've done in the previous two problems and find that the speed is 0.9999995 times the speed of light. Now, if we want to know what that is in meters per second, the precision there to 7 significant figures, we're going to need to not rely simply on the speed of light being 3 times 10 to the 8th meters per second. We can go to the front flap of the book and find, by definition, exactly the speed of light is 299,792,458 meters per second. So with that kind of precision, with the speed that we're finding, we'd better use that exact value. So when we multiply those, we get that the proton must be moving at 299,792,308 meters per second. So if you compare that with the speed of light, it's only 150 meters per second shy of the speed of light. And that is the end of the chapter 20 homework. Have a great day.